and onto the normal distribution. So if you thought that last formula was scary, to me this is like just bonkers. You have sigma in there, you have pi in there somehow, you have e, you have x and mu, and then sigma again. So not really sure why they put this in here. I mean, this is certainly the function. This is certainly what the normal distribution's probability density function is. This is the last time you'll see it. I'm not quizzing you on this. I'm not testing you on this. In this class, the main thing is you need to learn how to use the normal distribution, okay? Not use the function. So we're going to be calculating z-values. We're going to be calculating probabilities from the standard normal curve. And we're going to be doing all sorts of stuff with the normal distribution, but you will not need to know this formula, okay? So yeah, take a look at it and then just forget it. All right, so on to the normal curve. Everybody sort of has some prior experience with the normal curve, but we'll go ahead and get to it. Probabilities of the normal curve. There are an infinite number of normal curves. The shape of any individual normal curve depends on its specific mean and standard deviation. Okay, so when we work with the standard normal curve assumes that the mean is 0 and that the standard deviation is 1. So that's why we use z-values. We'll get into the z-values in a little bit, but this is to say that if we assume something is a normal distribution, it's allowed to have whatever mean it needs to have, and then associatedly whatever standard deviation it needs to have. But when we calculate a z-value, we call that normalizing the curve or standardizing the curve, or standardizing the value, and that's going to bring it back to the standard normal curve, which makes it a lot easier for us to find probabilities. It makes it so that you don't actually have to go to that crazy formula and figure out the probabilities based upon that. Okay, so we'll be standardizing it, and that's that. The highest point is over the mean, which is also the mean, median, or the mean and the mode. We actually saw this in, I believe, chapter 3. This was the graph that showed us the curves, and then you saw like mean, median, and mode in the symmetrical curve, and then you saw mean, median, and mode and what order it was in on curves that were skewed left or right. But so this normal distribution, the normal curve, is perfectly symmetrical, and the mean, median, and mode are all centered about the mean. They're all right in the middle there. Then we just talked about its symmetry. The tails extend off into infinity in both directions. And the area under the curve to the right equals the area under the curve to the left because it's perfectly symmetrical, and then each half has 0.5, which makes sense because then it means that the total probability is 1 of the whole thing. Okay. This is just talking about the position of the curves. The higher the mean is, then there's shifting that occurs. And then the taller a curve is going to have a smaller standard deviation. The wider a curve is going to have a larger standard deviation, which makes sense. So if you think large standard deviation, that means that there's higher variance, and that means that there's a higher spread of data. That's going to be a flatter curve with much a wider range of data. Okay, so this is going to be how we find probabilities with the normal curve. We're looking at an interval. So this is something we described when we were looking at the uniform distribution, which was another continuous one. So we have an interval from A to B. So this interval, this is the probability that X is between A and B. So this is just the visual representation of that. And here's just another slide that shows us that empirical rule, the plus or minus 1 standard deviation, 68% is going to be in there, plus or minus 2 standard deviations, 95%, and then plus or minus 3, 99.73. And then lastly, this is going to take us to the worksheet. But yeah, this is what a normal curve would look like with a mean of something that we either know or calculate and a standard deviation of something that we either know or calculate. And then this is showing the translation down into the standard normal curve. Okay, so we're going to use a z-score in order to turn something into the standard normal curve, because then we're going to be able to just go look up values in the back of the book and be able to determine probabilities. So we're going to get some practice in with just calculating z-scores. It's a very simple thing. As you can see by the formula, z is just equal to x, so minus mu over the standard deviation. So without any further ado, let's go to the worksheet. Okay, so we're going to look at number 4. And it's just asking us to calculate the z-scores based upon these x values. So we'll start with A. So z is equal to 25 minus mu of 30 all over a standard deviation of 5, which is a negative 5 over 5, which is negative 1. 2 is z is equal to 15 minus 30 over 5. Notice how the mu and the standard deviation don't change. It's just the x value that are changing in these. You get negative 15 over 5, which is negative 3. Z is going to be 30 minus 30 over 5, which is 0 over 5, which is 0. So that would actually mean that x is the mean. X is mu, which we can see is the case, right? X is 30, mu is 30, because there's no deviation there. Z is equal to 40 minus 30 all over 5, which is 10 over 5, which is 2. It's a positive 2. And for E, Z is equal to 50 minus 30 over 5, which is 20 over 5, which is 4. Okay, so that's the case. So that's that. That's how you calculate z-scores. It's that easy. Now, the numbers aren't always going to be as perfectly round and easy to work with as they are right now, but that's the concept. It's just z is equal to x minus mu over the standard deviation. So what we're doing is we're normalizing. So we're taking that value of 50 and we're just making it, or we're turning it into z equal to 4, which is to say that it is 4 standard deviations above the mean. Say z was equal to negative 4, that would be 4 standard deviations below the mean. Okay, so that's just a point on the standard normal curve. So go back here. This is just a shot of the table, and we're going to use this in a little bit. And these are just pictures of calculating the probabilities. So let me get us to, let's just start working on problems. You guys can go back and look at these slides as you would like, but the video is running a little bit long, so I'd rather just get into problems. Okay. So this is this part, number 5, is not about calculating z's. So this is assuming that we know z values, or we're given z values or whatever. This is about using those z values. So I'm going to do a few of these, and then I'll let you guys do the rest of them, because there are a lot here, and I don't think we need to do 9 of them. Okay, so A is saying find the probability of 0 is less than z is less than 1.5. And so all that's saying is what's the probability that z falls between 0 and 1.5. So what I'm going to do first is I'm going to draw a graph of what this is saying. Okay, so this is my best normal curve, sadly. And so because we're working with z means that we're on the standard normal curve. So we know that mu is right here, and that's equal to 0. So then we have 1, 2, 3, -1, -2, -3. Okay, and so now it's asking, well, what is the probability of z being between 0 and 1.5? So let's go find 1.5. And then let's find 0. 0 is right here. So we want to know the probability in this spot right here. Okay, so that's how. So this is how we would visualize this. So this would be the probability from 0 to 1.5 is represented by the area under the curve here. Okay, and so what we do in order to solve for this is we can find what the probability. So we'll say probability of 0 is less than z is less than 1.5. This is just going to be the probability that x is less than 1.5, or sorry, z is less than 1.5, minus the probability that z is less than 0. Okay? Think about that for a second. I'll let you think about that for a second while I draw the next graph. Okay? So think about why that might be. So 1, 2, 3, -1, -2, -3, 0. So the idea is that when we use the tables in the back of the book, so we're going to look up z values, and they're going to give us the probabilities that are cumulative. So probabilities from left to right. So it's going to start on the left-hand side, the negative side, and it's going to count up the probability all the way over to the z value. So when we look up z is less than 1.5, so this spot on the graph, when we find that value, it's actually going to give us the area under the curve of this whole thing all the way up until 1.5. Okay? So when we say that, if we're wanting to just find a sliver, so if we're wanting to find this sliver right here, then we'd have to minus off the part of the curve that is from here back. Okay? So then we would find this. So then we would minus off this piece, which would just leave us with this little sliver, which is what we're looking for up here. Okay, so we look for this probability value, and we look for this probability value, and we minus it off. And that's going to leave us this chunk right here. Okay, so we're going to go over to the table, and let me find the normal curve. Okay, so the normal curve looks like it is table A3. So the way that we do this, we're first going to find our first z value. So I believe our first z value was 1.5. And so we scroll down here on the z table, we look for 1.5. Okay, so now which number do we use in this whole thing? That's actually very easy to know. So this column just deals with one decimal place, so 1.50 essentially. So that's going to be these values, so all the way down here. But like say this was 1.51, that would be here. 1.52, that would be right here. 1.53, that would be there. So for just straight 1.5, we just have this value. So our value is 0.9332, so that's probability. So we write that here, 0.9332. Now we're going to be minusing off the probability that z is less than 0. I actually already know what that is, and you'll see why here in a second. But like, let's look at 0. Z is less than 0 is 0.5 exactly. And that makes a lot of sense. This makes sense because we already said that at 0, this is where half the data is over here and half the data is over here. So we know that there's 50% probability on this side. Okay? So we minus these from each other, 0.9332 minus 0.5000 is equal to 0.4332, and that's our answer. So that's the probability that z falls between 0 and 1.5 is 0.4332. Okay? Because this video is running pretty long, I'm only going to do one more. I'll just do B. B seems pretty easy. So we'll do B. Or it doesn't seem pretty easy, but it seems different, which I like. So B is probability that z is greater than or equal to 2. Now, in continuous distributions, greater than or equal to doesn't mean anything. Greater than or equal to is the same as greater than. That's only in continuous distributions, okay? In discrete, that would be something that we'd really need to look out for. But in a continuous, greater than or equal to, they're all the same. So this is easy because in our table, it gives us the cumulative probability. So meaning it's giving us everything up into a certain point. So everything from left to right. Okay? But now this is asking for the probability that something's greater than. So if we were to draw out our normal curve, which I am just awful at. Okay. 1, 2, 3, -1, -2, -3. This is asking for this point right here in the area right there. Okay, we know if we looked up the z value of 2 in the table, it would give us all the area back this way. Okay, but we need to know this area. So that's easy, right? We know that the total area under the curve is equal to 1, so we could just say, well, okay, then this is just going to be 1 minus the probability that z is less than 2, which is the value that we can look up in the table. So that's equal to 1 minus, and then we go to the table. We find 2, and that's 0.9772 right here. We go back. And that gives us 0.228. That's that. All right, guys, if you guys have any questions on this, please let me know in the discussion forums. If you need to see more examples, I can write some up. Actually, what I'll do is I will just put up my version of this as a PDF, and I think that'll be helpful. I just think it'll be a big time waster if I'm just sitting here walking through these on video. But be sure to ask questions. And yeah, I'll be sure to focus on this a little bit more in the review, but just wanted to get through some of these. Thanks so much, guys, and Next time we will cover Poisson and exponential.